2 years after Mount St. Helens erupted, the pumice plain directly north of the crater was the most sterile landscape in North America. 6 square miles of gray, porous volcanic rock. Chemical analysis of the surface returned 0 measurable carbon and 0 nitrogen, the 2 elements every living cell on the planet requires. Standard ecological models predicted recovery would take centuries, building soil 1 millimeter at a time through the grinding patience of lichens on bare rock. The fix involved helicoptering a handful of pocket gophers onto the ash, letting them dig for exactly 24 hours, and removing them. Within 6 years, 40,000 plants had established in the exact footprints of those 24-hour enclosures. The surrounding plain remained virtually barren, and when scientists returned 4 decades later to core soil samples from the same coordinates, the chemistry was still measurably different from everything around it. The answer has almost nothing to do with the holes. On the morning of May 18, 1980, a magnitude 5.1 earthquake collapsed the entire northern face of Mount St. Helens, triggering the largest debris avalanche in recorded history. The lateral blast that followed, superheated gas and pulverized rock traveling at over 600 miles per hour, flattened old-growth forest across 230 square miles. 57 people died. 4 billion board feet of commercial timber vanished in minutes. The worst of it hit the pumice plain. Successive waves of superheated volcanic flow, reaching temperatures above 1,500 degrees, buried the ground under deposits of ash and pumice up to 130 feet deep. Everything above the surface was incinerated. What remained, visible in the decades of footage shot across this stretch of the mountain, was a flat, pale gray expanse of volcanic glass. Porous enough to drain any rainfall within minutes. Bare enough to swing between scorching heat and near-freezing cold at ground level, and too chemically empty to anchor a single root. The reason it stayed that way comes down to one variable. The eruption didn't just destroy the surface, it sealed what was underneath. Before 1980, this had been old-growth coniferous forest, anchored by deep soil accumulated over millennia. Soil rich with dormant fungal spores, bacteria, and organic nutrients. The volcanic deposits locked all of it beneath 10 to 25 centimeters of sterile rock. The dead surface couldn't reach the living ground below. The living ground couldn't reach the surface. Seeds arrived on the wind. They germinated. They starved. Without the symbiotic fungi that healthy plants depend on to extract water and nutrients from raw mineral soil, each seedling was running on the energy stored inside its own seed. In sterile pumice, that energy ran out fast. Elsewhere on the mountain, the proof was stark. Old-growth forest buried under the same ash recovered within years, because its surviving trees still maintained fungal networks underground. Clear-cut zones right next to them, stripped of trees and their fungal partners before the eruption, stayed barren for decades. Same ash, same rain. The only difference was biology. The pumice plain was the worst version of that problem. No trees, no roots, no fungal networks. The cure was buried directly under the disease, separated by a barrier less than a foot thick. And the reason that buried soil had survived at all, despite surface temperatures hot enough to melt glass, was the calendar. The mountain erupted in mid-May, when deep winter snowpack still insulated the higher elevations. The ice absorbed the heat of the surface flows while shielding the ground just centimeters below. Everything the surface needed was right there, preserved by an accident of timing. The question was how to breach the barrier. 2 researchers proposed an answer. Michael Allen, a microbiologist from UC Riverside, and James McMahon, an ecologist from Utah State, chose the northern pocket gopher. Compact, thick-bodied, with oversized front claws and forward-angled incisors, evolved specifically to chew through compacted earth. Its lips seal shut behind the teeth, so it doesn't swallow what it's excavating. A single individual can displace up to 500 pounds of soil in a month. The whole animal weighs about 160 grams. The ones they captured from intact forest on the mountain's unblasted southern flank and helicoptered onto the pumice plain were, by all published accounts, furious about it. The research record describes them as grumpy, moody, and deeply unhappy about being deposited on a volcanic wasteland. Each gopher was placed inside a 1-meter square wire enclosure, built around an isolated lupine seedling, one of the few plants that had managed to germinate from wind-blown seeds in the ash. 1 gopher in 1982, 8 or 9 more in 1983. Each was allowed to dig for exactly 24 hours. After one day, the researchers returned by helicopter, recaptured every animal, and flew them home. The stated goal was not landscape restoration. It was a localized test of soil mixing, whether a burrowing rodent could marginally improve survival for a few isolated plants in a few square meters of ash, a few rodents, a few wire squares, a single day, on a landscape where the expected timeline was centuries. In those 24 hours, the gophers did what pocket gophers do. They dug aggressive, relentless excavation through the volcanic crust, pushing the buried pre-eruption soil to the surface in fan-shaped mounds that reshaped the flat ground into a patchwork of tiny ridges and hollows. Those hollows would matter. They trapped wind-blown seeds and held moisture against the desiccating surface conditions. But the gophers also did something no bulldozer could replicate. Their fur was coated in dormant fungal spores from their home forest. Their digestive tracts carried the same. As they moved through the legacy soil and deposited fecal pellets into the sterile pumice, they delivered concentrated packets of viable fungal spores, bacteria, and raw organic carbon directly into ground that contained none. Then they were removed. And for 2 years, nothing visible happened. Between 1983 and 1985, the Pacific Northwest entered a severe drought cycle. Across the broader blast zone, seedlings that had colonized the ash via wind dispersal died in enormous numbers. The pumice couldn't hold moisture. Rain drained straight through. On the surface, the gopher plots looked exactly like every other patch of gray rock on the plain. But underneath, the clock was running. The fungal spores deposited in the gopher waste germinated. Microscopic threads radiated outward through the mineral ash and found the roots of the struggling lupine seedlings. Once contact was made, the exchange began. The fungi mined phosphorus and water from deep in the pumice and delivered them to the plant. The plant fed photosynthesized carbon back to the fungus, and because prairie lupines are legumes, the same family as beans and peas, they carry bacteria in their roots that can pull nitrogen directly from the air. The fungi provided the water and phosphorus the lupines needed to run that process. The lupines provided the nitrogen the soil had never contained. For the first time since the eruption, something was building instead of breaking down. By the late 1980s, the lupines inside the gopher plots had exploded in number. They reproduced and eventually died, and their decaying biomass created the first post-eruption layers of organic matter on the pumice surface, dark, moisture-retaining soil where there had been nothing but gray rock. That new soil trapped wind-blown seeds of secondary species. Those seeds germinated, grew, added more biomass. The cycle compounded. When researchers returned in 1989 for a full vegetation count, they documented 40,000 individual plants growing inside the historic gopher enclosures. The surrounding pumice, same weather, same wind-blown seeds, same sunlight, held almost nothing. The entire federal post-eruption effort on the pumice plain, backed by helicopters and thousands of pounds of aerially sprayed grass seed and synthetic fertilizer, hadn't produced results in the deep ash zones that matched 24 hours of work by animals that weighed less than a baseball. Through the 1990s, the plots stopped being isolated green patches and started functioning as anchor points for the broader landscape. The dense vegetation stabilized the loose ash and halted local wind erosion. The accumulating organic layer allowed woody shrubs, willows, and early conifer seedlings to take hold, species that couldn't survive in raw pumice but thrived in the enriched soil the lupines had manufactured. The system also attracted friction. Roosevelt elk herds, drawn by the only concentrated forage on the pumice plain, moved in and began browsing heavily. They stripped young willows. They rubbed antlers against conifer saplings, snapping them at the base. For anyone tracking tree recovery, the elk were a genuine setback, holding the landscape in a state of permanent meadow, delaying the transition to closed canopy forest. That pressure continues today, but the elk were also importing biology, nutrient-dense dung, seeds from intact forest carried in fur and through digestive tracts. The browsing slowed the canopy. The inputs accelerated everything else. And quietly, wild pocket gophers from intact populations on the mountain's unblasted southern slopes began migrating onto the pumice plain on their own, colonizing the enriched ground the original deployment had created, and pushing the soil mixing process outward at the edges. It was the first sign the system didn't need anyone's permission to expand. And then the molecular data came back. For 2 decades, the working explanation of the gopher experiment was mechanical. The gophers broke the ash crust. They mixed soil layers. They gave plants physical access to buried nutrients. A useful rodent with strong claws, that was the narrative. In 2024, a research team from UC Riverside, the University of Connecticut, and Yale published a study in Frontiers in Microbiomes that dismantled that explanation completely. Using DNA sequencing on soil cores extracted from the exact coordinates of the 1982 and 1983 enclosures, 40 years after the gophers had been removed, they found something the mechanical model could not account for. The microbial communities in the gopher plots were not just richer than the surrounding pumice, they were structurally different. Higher fungal diversity, more complex bacterial architecture, measurably elevated carbon and nitrogen concentrations. 4 decades later, the biological fingerprint of those 24 hours was still written into the soil chemistry. The gophers hadn't been plows. They'd been delivery vehicles. The holes mattered, but what mattered far more were the microscopic fungal spores carried on their fur and deposited in their waste, the living architecture that connected to plant roots, mined the mineral ground for nutrients, and built a self-sustaining biological network from nothing. The experiment had never been about soil mixing. From the first hour, it had been a microbial rescue, the reintroduction of an invisible biological system to a landscape that could not function without it. By 1987, just 5 years after the first enclosure, carbon in the treated soil had climbed from 0 to 840 milligrams per kilogram. Nitrogen rose from 0 to 53. The surrounding pumice hadn't moved. By 2000, carbon had surged to 4.6 grams per kilogram. Nitrogen reached 384 milligrams per kilogram. 20 years of identical weather on adjacent ground had done nothing to close the distance. It was still widening. The total biological labor required to start that trajectory weighed less than a pound. The material cost was helicopter fuel and wire mesh. No fertilizer, no follow-up, no maintenance budget for 4 decades. The system has run itself since the enclosures came down. From those few gophers, dropped onto a dead volcanic plain for 24 hours in the early 1980s, came a biological signal that is still compounding across the mountain today. The tunnels were the vehicle, the fungi were the payload, and the payload is still running. The pumice plain is still recovering. The soils are geologically young. Elk browsing still holds the canopy back. But the biological engine underneath is permanent, self-sustaining, and expanding outward from the same coordinates where a few unhappy gophers dug for 24 hours in 1982. And the principle underneath, that on sterilized ground, reviving the invisible microbial network has to come before anything else, carries implications far beyond a single volcano. Start with the microbes. The plants follow. If this kind of engineering is what brought you here, subscribe. There is more coming.